Up next, we're going to talk about a couple of ideas. The first idea is the idea of extrapolation. We're going to define extrapolation as using the regression line to make predictions beyond the range of observed data. For example, here I have the ages and heights of 6 people. I have a 4-year-old who is 35 inches all the way up to a 15-year-old who is 70 inches tall, and I've got some people in between. Let's say we want to use this data to predict the height of a 30-year-old. The first thing I need to do is get my regression line equation. To do that, I'll first put my data into the calculator by hitting Stat and then Edit. I already have those 6 ages and heights here. To get my regression line, I'll just now hit Stat once again, go over to Calc, and I want number 8. So here's my list of data values. Y is in the form A plus BX. A is 25.8 if we round it up 1 decimal place, plus 2.9x for B if we round to 1 decimal place. So to make my prediction for a 30-year-old, I'm just going to plug 30 into my equation. I'll take 25.8. I'll add 2.9 times 30 in for the x, and that gives me 112.8. We would use this data and we would predict that a 30-year-old will be 112.8 inches tall. Well, if we put that in feet and inches, if we divide that by 12, we get that person is 9.4 feet, which that doesn't make any sense. I wouldn't think a 30-year-old will be 9.4 feet tall. That's not possible. And so this would be an example of extrapolation. I'm making a prediction outside of my observed data. I can't be certain what may occur outside the observed data range. So it's dangerous. And many times, just like this time, the extrapolated value doesn't make sense. We want to avoid extrapolation if we can. I could make a prediction for an age in between 4 and 15. That should be fairly accurate based off of this data. But anything outside of that, a 1-year-old or a 2-year-old or a 30-year-old or a 40-year-old will not be that accurate. We could make a prediction for a 12-year-old or for an 8-year-old. That should be okay. That won't be an extrapolation. But when it's outside of the data set, that's extrapolation. The other idea I want to talk about in this video is regression toward the mean. And according to regression toward the mean, values are more likely to return closer to the mean rather than to move farther away from the mean. This linear regression, this line of best fit that we have, this is a line of averages. And so what we tend to see in the real world is that when we see an extreme value, in the next turn, that value is more likely to be closer to the average or to the mean rather than to move further away and be more extreme. Now this is not always, but it's more likely most of the time. So a couple examples to sort of cement this. The average height of a man is 69 inches, it's 5'9". But then there's NBA star David Robinson. He's 85 inches tall, that's 7'1". So he is very tall. He would be classified as an outlier. David Robinson's retired. He has a few kids. His son, Corey Robinson, who plays football for Notre Dame, is 76 inches. He's 6'4". So we see that while David Robinson was very tall, his son didn't get even taller. His son wasn't 7'3" or 7'4". but he was a little bit shorter. He was closer toward the mean. He was 6'4". Values are more likely to return closer to the mean rather than move farther away from the mean from that average. Another example, sports related, in the NFL, the average yards per carry for a running back is about 4.2 yards. Jamal Charles is a running back. He played for the Kansas City Chiefs, and in 2010 he had a great season. He averaged 6.4 yards per carry, so that's way above the average. He was hurt in 2011. He didn't play a full season, but when he came back in 2012 and played a full season, he was only down to 5.1 yards. So he's still above the average, but he's closer to the average rather than moving farther away. We don't see 6.6 and then 6.8. We don't see new records being broken every year. And that's how we explain regression toward the mean.